Thanks a lot. It's a great pleasure to be here and share my work. So this presentation will be a kind of a continuation from what Jörg and Stefan already discussed on how we use molecular dynamics to study electrochemical systems, especially focusing on how we treat the different electrode potentials. Uh, but in this talk, I will focus more on some more recent developments. So let's get started. So I think at this point, I don't need to motivate why we are interested in study solid-liquid interfaces. As we all know, they are relevant in a lot of technologically important applications, such as electrocatalysis, fuel cells, batteries, biomedical applications, and also corrosion. And as we all also have seen already throughout this workshop, actually, what is happening across this solid water interface can be very complicated. So on the solid side, you can have different surface phases or defects. So that's something of consideration. And also on the water side, you have the electric double layers. You have absorbed ions as well as these diffuse layers and the buildup of the electrostatic potential. But from ab initio molecular dynamics or AMD, what we can study is only a tiny fraction of what is happening. So mostly we focus on where the reaction is really happens. So really this very small box at this interface. And on the right, this is a typical type of simulation cell that we have when we do this kind of study. So of course, there are many different ways to simulate the electrified solid surface. But this is the main method that we use in our group, which is a computational counter electrode. So on the one side, we have the metal or our working electrode. And on the other side, we have a neon computational counter electrode. And by changing the nuclear core charge of the neon, we can set up this kind of a long-range charge transfer, where by having this double capacitor setup, we build up a constant electric field across this water slab. Um, so so then there are still challenges related to when we want to do this kind of voltage controlled AMD, as this has also been mentioned in by Jörg in his talk. The main reason is that, as we all know, experimentally, these experiments are done at constant electrical potential or constant electrical charge. But when we go down to these very small simulation cells, we go into the region where we need to also consider the potential fluctuations due to this very small scale that we are simulating. And indeed, in this case, we need to consider there is this distribution of the electrical charge and the potential to capture the correct reaction dynamics. And this led to the development of the thermal potential stat by Florian and Stefan. So I won't go into the details of this because this was almost already covered. But the main point is that in this thermal potential stat, similar to a thermostat, you have a potential control term which drives the system to the target potential, but then you also have this fluctuation term. So when this thermal potential stat was first developed, this was done using by directly modifying the VASP code. So Florian did all this implementation. But here there's definitely still some barriers because if you want to use this specific method, you need to get this patch to the VASP code and compile this specific version of VASP that will allow you to do this simulation. So we definitely see that there is still a barrier to really use this method for the broader community. And then there is always this challenge of the system size and timescale limitation of AMD, as has also been covered a lot already in this workshop. So I just show one example here where we try to study the magnesium dissolution on this vicinal magnesium surface where we have this kink atom. So we chose this kink surface because in principle, it should make the dissolution event happen faster. And we performed the AMD simulation on this interface for 50 picoseconds, as you can see from this animation. Indeed, this kink atom will go out quite a bit. But in the end, there is a kind of anchoring effect of this OH at this interface, which prevents the magnesium to form the full solvation shell. So in this time scale that we can do with AMD, we'll never see the full dissolution of this magnesium atom. So then there is this, of course, you can try to drive this kind of surface reaction with enhanced sampling, as you have already seen in Alfredo's talk. But even in that case, to sample the free energy surface, you need trajectories on the scale of nanoseconds. So that is still not doable in an AMD simulation. So, so that's why there is a strong motivation to go to this machine learning potential-based AMD, where you can achieve a similar accuracy with the DFT training data, but with a much reduced computational cost. And for this, then you can really study these surface reactions. So today my talk will compose of two parts. The first part will be on the ab initio side, where we try to develop a more easy and straightforward way to get electrostatic potential into a DLT simulation. This is achieved by utilizing the newly released Python plugin in the VASP software. And the second part, I will talk about our vision of how we can do this kind of potential control the molecular dynamics using machine learning potential. Okay, so let's get started with the first part. So getting an external electric potential into a DFT simulation is actually not a new problem. It is already a very common practice. And I want to show two examples here. The first is dipole correction. This was developed by York already in 1992. And the idea is that due to the periodic boundary condition of the DFT simulation, you can have this spurious electrostatic interaction. For example, in this setup where you have an asymmetric surface slab, so then you will have this electric field in the vacuum region. And the idea of the dipole correction is very simple, which is basically in the vacuum region, you will insert a dipole, which will cancel out the total dipole of the system, making the whole system dipole zero. And then in this case, you retrieve this behavior where you have the flat potential in the vacuum region. So this is available in almost all common DFT code already. It is so easy to use that sometimes people even misuse it. And the idea is that if you intentionally add a dipole that is larger than the supposed compensating dipole, you can build up this kind of constant electric field across the simulation cell. So this is the way how people do this constant electric field calculation in DFT. And the other case, which is also discussed a lot already in this workshop, is implicit solvent. So I think you are all very familiar with this concept, which is basically you do not explicitly model the electrolyte, but model it as a screening medium. So what is in common between these two methods I'm listing here is that in both cases, the way you're adding this external electrostatic potential into the DFT is by calculating the corresponding potential of these externally inserted charges. And then these external potentials are added to the Kohn-Sham Hamiltonian. And in this way, the DFT you can do DFT calculation with this kind of external electrostatic potential. So both of these methods are well established, and they are available in DFT codes, for example, VASP. However, they are very difficult to customize. So in VASP, of course, on the dipole correction side, you can do a calculation with a constant field. And in the implicit solvent side, you can tune these defined parameters of the implicit solvation model. But then if you want to customize this kind of external electrostatic potential, it becomes very difficult because you really need to go into the DFT code and then change it from there, making the use of this, so making the extension of these methods very difficult. So we got into contact with VASP team. This was motivated by that we want to extend the implementation of the thermal potential stat. And what they provided is an interface between VASP and Python. And the idea is very simple. So during a DFT run of VASP, it will expose some of the physical quantities to a Python plugin. And then you can write a Python functions that changes these quantities, such as the forces, energies, number of electrons, external potential, and so on. And in this way, you can very easily tune the quantities, such as external potential. And in this way, do these kind of simulations with quite great flexibility. So I just want to show you a very simple example of how you can use this. This is already available in the very recent version of VASP 6.5.0. And the way you use it is that in the input file of VASP, so in-car file, you will tell VASP that to invoke the Python plugin of these given functions. For example, if you want to change the electrostatic potential, there is this function called local potential. So you just say in this in-car file, you say that I want to invoke the local potential function. And then you will have this additional input file called VASP-plugin, which will change these quantities. So here you define the function of local potential, and there are predefined quantities that you can access in this function. The ones that you cannot change are called constants, and then the ones you can change are called additions. So the way you can add the external field is just by this single line, which is additions dot total potential plus equal to the delta potential that you want to add. So as simple as that. However, when we first got in touch with the VASP team to try out this plugin, we just naively added the external potential, as I have just shown. But what we found is that the energy and forces that we got out of these VASP calculations are quite wrong. So we did the very simple test of just one single hydrogen here in a constant potential. So supposedly it should not change the energy of this system. However, we see that if you just take the output of VASP, you see this very strong dependence of the energy with this constant potential you're applying. And this is also true for the force. If you put this hydrogen atom into a constant field, so in principle, because the hydrogen atom is neutral, the field should be close to zero. But again, we see a very strong dependence. And it took us quite some time to figure out what is accounted for and not accounted for in VASP. And it turns out what is missing in the VASP as it is the interaction between the external field and the nuclear core. But luckily, this is very easy to correct because in these DFT calculations, the nuclear cores are treated as point charges. So what we need is just a correction to the energy and forces of how these point charges will interact with the external field. So then this is how the input would look like. So in addition to changing the potential, we also correct for the energy and forces. The correction of the forces is done in this force and stress function, where again, you use this kind of syntax. You say the additions of forces is plus equal to the delta force that you calculate. Okay. So then we have a working version of now you can add any kind of external potential in a DFT calculation. What we did is we replaced the neon counter electrode now with a charge density electrode. So instead of having explicit neon atoms to hold the counter charges, now we just put a charge density at this position instead. And then the potential corresponding to this charge density is added into a DFT calculation. So in this way, we can achieve the same kind of computational setup as a neon counter electrode. So again, build up a constant field across this lab system. And one of the advantage of moving away from the neon is that when we have the neon electrode, the maximum electric field magnitude that we can apply is limited by the band gap of the neon. So if you have a too large electric field, the Fermi level will go into the valence band or the conduction band of neon, and this would cause a dielectric breakthrough. So by replacing neon with just the charge density, this limitation is lifted. And here I want to show you just a model system of a gold 111 surface where we put the counter electrode here. And you can see that by changing the magnitude of the charge on the counter electrode, you can achieve this different magnitude of the electric field in this vacuum region. Now I want to show you one example how we can use this setup to study a realistic physical problem, which is the field evaporation of lithium. This study was led by Xiang and Christoph. And the motivation was that from experimental side, in the atom probe tomography, they see inhomogeneous field evaporation of lithium. So this is very different from the expected behavior of other types of metal, where you would expect a homogeneous distribution. But here in this figure, you definitely see that there are these local hotspots forming, indicating there is a strong surface morphology change when you do the field evaporation. So Xiang studied this field evaporation energy profile with Sphinx, applying different magnitude of electric field up to 1.3 volt per angstrom. So what he did is he studied this add atom going out of the surface on this 110 surface. And this plot shows the energy versus the height of this add atom. And as you can see, even at this maximum field of 1.3, you still have quite a significant barrier for this evaporation to happen, about 0.13. However, what is very interesting is that he also looked at the energy profile when you have this kind of lateral diffusion. So initially, this add atom is sitting on the on top side. And then at no field is thermodynamically not favorable for this lithium atom to go into the bridge side. But you can see here, when you increase the field magnitude, at some point, it is thermodynamically more favorable for the lithium to be on the bridge side, indicating there is this barrierless diffusion laterally of this on-top lithium add atom. So we were intrigued by this observation, and we indeed did AMD simulation using this newly developed implementation with a VASP-python interface. So this is what we did. We simulated a kink lithium surface. This is a 952 steps lithium. And this white atom here is a kink atom. And the electric field is applied in the surface normal direction. So this is the direction of the field. So if we do the simulation with no field, there's not much happening. We don't see much. So the step surface stays as it is. However, when we add this magnitude of electric field, during this 5 picosecond of the AMD simulation, we see this spontaneous desorption of this kink atom going away from the step. So this is a top view before and after. So indeed, you see that we see this lateral diffusion of this kink atom, confirming what has been seen previously in this energy profile, showing that at some point, due to the application of the electric field, there is this change of surface morphology of lithium and the formation of a gas or liquid-like surface under this electric field. Okay. So now I want to go back to the implementation of the thermal potential stat. So previously, the examples I was showing was not changing the field during the AMD simulation. But if you want to change it, as what we see, if we want to include the field fluctuation, this is also very simple. So we invoke a third function, which is called occupancies. So this function is called at the end of every molecular dynamic step. And in this function, you can change the applied bias, which is basically translating this equation for the electrode charge into this Python function. And then this function would update the applied external potential at each MD step. And therefore, you can do any kind of potential control that you want in an AMD simulation with very easily and also with great flexibility. Okay, So far, I have focused on this double capacitor setup, where you have the working electrode and the counter electrode. But with this VASP-python plugin, you can really do any kind of external potential that you want. And one of the applications that can be of interest is the implicit salvation model. So here, I just want to show a simple example where we did the QM mean field salvation model of magnesium 2 plus ion. And the idea is very simple. So in the DFT calculation, we only have the magnesium 2 plus, and then the screening field of water is simulated by a classical force field. We do a long trajectory of the classical force field calculation, and then we get an average electrostatic potential of water. This average potential is added back to the DFT calculation. So this is similar to an implicit salvation model. And here, this is the total charge density that we're getting. So showing, you see these rings around this magnesium 2 plus. These are showing the salvation shell forming around this magnesium ion. And then on the right, we have the potential profile comparing the vacuum case versus the screened case. So in the vacuum case, you have this parabolic behavior. This is caused by the 2 plus charge of the magnesium. But then once you add this salvation potential from water, you see these oscillations around the magnesium, again showing the formation of the salvation shell. And then the potential goes to flat potential when you go far away from the magnesium 2 plus. So then this kind of VASP plugin allows you to do a very fast change if you want to do different implicit salvation models, which was not provided by VASP as it is. So then now I come to the summary of the first part. Hopefully I have shown you that with this newly released VASP-python plugin, now we have much more flexibility in how we can do this DFT supercell calculation with arbitrary electric field. And these will allow us to study various field-induced processes at surfaces and interfaces. If you are interested in this work, you can scan this QR code for our archive preprint. And we are also uploading these scripts and examples in our online GitHub repository, so you can definitely check it out. With that, I go to the second part of the talk, which is centered around the machine learning potential. So I think at this point, I don't need to say much about why we are interested in it. But of course, we are seeing that there is a growing interest in using machine learning potential, especially with the development of the universal ones, which promises to cover the whole periodic table. But as the basis of these machine learning potentials, most of them have this kind of structural descriptors, which is basically describing the atomistic environment of a given atom within a certain cutoff radius. So by design, these structural descriptors are short range. And in these most commonly used types of machine learning potentials, these structural descriptors are put into a machine learning model, which would predict the energy and forces of the given structure. And of course, a big limitation is that long-range electrostatic interaction is only implicitly accounted for. So they do not allow us to do this kind of voltage-controlled molecular dynamics as we want. So in this workshop, we have already seen this deep potential. There are different ways of including these long-range interactions into machine learning models. And this deep potential, how it does this is by predicting the position of the maximally localized Wannier functions. So for example, for water, it will be predicted as something like this. So it will have the 3 ions, 1 oxygen, 2 hydrogens. And then additionally, it will be associated with 4 Wannier centers, each corresponding to 2 electrons. And in this way, you have a machine learning model that predicts the position of these Wannier centers from the structural descriptors. And from this local charge distribution, you can then calculate the long-range electrostatic interactions. So this long-range part is separated from the short-range part. And then you can have 2 separate models describing the 2 parts. And then by summing them together, you have the full model, which also includes these kind of long-range interactions. And in this wonderful talk by Annabella Soloni, we have seen how this deep potential model is used in simulating this interface between titanium and water. And what we were very excited about is that they were showing this deep potential model can reproduce the electrostatic potential as predicted by DFT. So then we were motivated to see whether they can also reproduce the electrostatic potential once we have a long-range electric field in our setup. So then we just went ahead and we did it on this very simple test system of nano-confined water. So this is just the water sandwiched between two neon electrodes. And if you look at the electrostatic potential for one single frame, it will look something like this. So on these two sides, you have this dips, which corresponds to the neons. And then in the middle, you have these oscillations corresponding to the water. And in the vacuum region, we have the dipole correction, which gives us also the total dipole moment of the system. And what we can do is that by tuning the nuclear pole charge of the neon, we can have this long-range charge transfer between the two neon electrodes. And in this way, build up an electric field across this slab. So if you do this minus Q and plus Q, and you put this in a vacuum, this would correspond to this phi external. So again, a constant electric field throughout the water slab. Now, if you look at the DFT electrostatic potential profile after you do this charge transfer, it will look something like this. So this is freezing in the atomic configuration, only looking at the electronic response. Then if you take the difference between the potential with the field and without field, you get this dashed line, which is the delta phi. And as you can see, delta phi is not exactly the same as phi external because of the electronic screening of water of the externally applied electric field. And this will correspond to the high frequency dielectric constant of water, which is about 2. So the field corresponding to delta phi is about half of what you get from this phi external in vacuum. And then we performed the Wannier function calculation on this simulation cell with the applied electric field. And then we reconstruct the electrostatic potential with these Wannier centers. This is represented here by the green line. And as you can see, these Wannier centers indeed can reproduce the electrostatic potential especially in the long range. So if you look at this total dipole moment, you can see that there is a good agreement between the DFT and the Wannier center simulation. So now what we did is that we just similar to the deep potential model, we trained the machine learning model that would predict the individual water molecule dipole from this data set where you have this applied field across the water slab. And our machine learning model, which I write here, ML Wannier Center, they can predict the Wannier Center positions with very good accuracy. So this is similar to the accuracy of the deep potential model, comparing the DFT individual water molecule dipole versus the machine learning predicted one. And of course, when you have this good local accuracy, you would expect the model would also reproduce the long-range electrostatics. However, when we reconstruct the electrostatic potential with the output of this machine learning model, what we found is that even though locally you have good agreement, in this long-range field, there is a quite significant deviation from what you're getting from DFT. This is also represented if you just look at the macro dipole. So now I'm plotting this comparison of the macro dipole of the system, comparing the machine learning result from the DFT with the different frames. So these are 20 frames of data I'm showing. So what you can see is that there is a systematic deviation in the macro dipole that we are predicting if you take the result of this machine learning model learning from the local Wannier center positions. So this is definitely not just a noise, or this is not a noise, because as you can see that we not only have an offset, but we also have a shift in the slope if you plot this data together. So definitely indicating there is something physical about this deviation. And what we eventually figured out is that the origin of the error comes from a lack of the electronic polarization. So I want to explain a little bit how water is responding to the electric field. So this is the water model. If you want to measure the dipole moment of water, what you do is that you take the center of the core charges and then take the center of the electron charges, and then you measure the displacement between the two. Once you have an electric field applied, the center of the electron will be displaced. So this is this REL under the electric field. And now we show this plot where we plot the dipole moment of individual water molecule as a function of the applied external field. And these blue dots show the distribution of these individual water molecule dipole. What you can see is that on this scale, you almost do not see any change in this individual water molecule distribution. This is also shown by this blue line where I show the average of this shallow blue dots. And you can see that it is almost flat. So on the individual water molecule level, you almost do not see the effect of this electric field effect. However, if you look at the total water molecule dipole, you see a very strong dependence of the field. So this is on the macroscopic scale. There is this factor of 2 caused by the electronic polarization of water. And this can also be shown if you measure the displacement between these charge centers. So on average, the distance between the electron and core centers is on the order of 0.08 angstrom. But if you apply this field strength of about 0.2 volt per angstrom, which is already very large, the displacement in the electric field is only on the order of 0.001 angstrom. So this is orders of magnitude smaller than the static dipole moment of water. So that is when we say the signal of the field response is much, much smaller than the thermal noise. And in this case, the machine learning model cannot capture this kind of long-range effect caused by the electric field. And indeed, we can also understand better this result of the electrostatic potential we were getting from the machine learning model, which is that because now we are lacking the electronic polarization, what we get, the field that we are getting in water is almost the same as the field that we're getting in vacuum. And this is twice to the field that we're getting if we have the electronic polarization as we have in DFT. So after having figured all of this out, we want to develop a method which can give us an accurate macro dipole, which is a representation of the long-range electrostatics. And hopefully in this way, we can do a voltage-controlled MD with machine learning potentials. So this inspired us to propose a new method, which is learning directly from the macro dipole, instead of learning from the local Wannier centers. This method, we call it scalar macro dipole integrate learning, which is the acronym SMILE. And the idea is that, again, we have the structural descriptors of individual water molecule. And then we would predict the individual water molecule dipole from these structural descriptors. But the constraint that we're adding is only that the sum of the individual water molecular dipole should be the total dipole. And in a way, this is analogous to how common machine learning potentials are learning the energies. So in DFT, we only have the total energies. But then in machine learning potentials, you would learn these atomic energies based on the structural descriptors. And the constraint is that the sum of these atomic energies should be equal to the total energy. Then we just naively applied this constraint and constructed a machine learning model. This model we call the SMILE 0. And I want to show the behavior of this model on this kind of slightly more complicated system. So we still have the two neon electrodes, but here we also have a magnesium 2+ ion, and the compensating charges are sitting equally on the two neon electrodes. What we found is that the machine learning model can indeed predict the total dipole of the system once they are trained on it. However, the model shows very bad transferability, as shown here by the test data. As you can see, it's quite all over the place. And what is also very interesting is that the SMILE 0 model gives the wrong screening behavior. So that is why we go to this magnesium 2+ system, because here you can observe the screening behavior of water very clearly. In DFT, due to the large dielectric screening of water, so this black line shows the position of our magnesium 2+. The potential around the magnesium 2+ is almost flat, so you do not see this electric field building up. But this is, of course, not the case of the SMILE 0 model, where you see that you have this kind of V shape around this magnesium 2+. So definitely, in both criteria, you can see that the SMILE 0 model is not working. And why is that? This also took us quite some time to understand. But the origin of the error again goes back to a lack of the electronic polarization. So previously, we have seen that on the individual water molecule level, this electronic polarization signal is much smaller than the static dipole of a water molecule. However, since all the water molecules would have this kind of small displacement, when you add them up, they have a very large macroscopic effect on the total dipole. And if you separate the total dipole into the two parts, one associated with the electronic polarization and one associated with the local, the total would just be a fraction of the local dipole summing up together. And this is associated with the susceptibility of water, which is epsilon infinity -1. For water, this is about 1. However, since the machine learning model cannot capture this electronic polarization part, so instead of separating the total dipole into the static part and the electronic polarization part, it instead just scales the static part. And this is shown by this result if we plot the magnitude of the individual water molecule dipole predicted by the SMILE model comparing to the result from the Wannier center model. So for water molecules in water, the average water molecule dipole is supposed to be around 0.6. But here you can definitely see that the SMILE 0 model gives you only a fraction of that. So this explains why when we plot the electrostatic potential, the SMILE 0 water gives you a very weak screening behavior. So then after figuring out why the model is wrong, we improved it by now taking into account the electronic polarization. And now this is what we call the SMILE model. So instead of saying that the individual dipole will just sum up to the total, we say that the local or static dipole moment of the water molecule, when you sum them up, this should be the total subtracting the contribution from the electronic polarization, or 1 plus psi times the total dipole. And now we plot the RMSE on the total dipole of the system versus psi. So this is treated now as a free parameter. And as you can see here is that especially the test error depends strongly on psi. And we achieve optimized model at a psi value of around 1.1. And this is close to the psi if you compute it for the DFT water, which is again about 1. And if you use this correct value of psi, what we see is that now the SMILE model can really reproduce also the magnitude of the individual water molecular dipole. So this goes back to about 0.6, which is expected. And now if we plot the test arrow and also plot the electrostatic potential, you can see that the SMILE model now achieves a good transferability. And also now the electrostatic potential, if you look at this, it reproduces the DFT data, both in terms of the long-range electrostatics and also the local behavior. So an advantage of our model is that now we actually do not have to do a Wannier function calculation on the system because we only need a scalar quantity, which is the total dipole moment of our system. And this also allows us to have an easy extension to atomic charge model instead of the dipole model. And the idea is, again, instead of having the mu I, the individual dipole moment of water molecules, we just say that if we sum over the QIZI, we should again have this constraint. And then we add another constraint, which is the global charge neutrality. So if you sum over all the atomic charges, you should get 0. And this allowed us to perform this study on a more complicated system, which is what I've shown initially, the Vicinal magnesium surface. So for this system, we performed the AIMD of around 50 picosecond, initially under open circuit condition and afterwards under anodic bias. This is how the electrode charge is evolving. And we build one model to, this is the electrostatic potential that we're getting. The dashed black lines are showing DFT results. And as you can see that in the open circuit condition, in the middle, you are almost flat. And in the anodic condition, you have this buildup of the electric field inside water. And by having this SMILE model, indeed, we can reproduce this electric field that is building up. And in this way, we have the correct macroscopic field predicted. And with that, I come to the end of my talk. So hopefully I have shown you that the machine learning models learning from the local charge distribution fails to capture the electron polarization induced by a long-range field. And this leads to a systematic deviation if you look at the predicted macro dipole. And we are able to solve this problem by directly learning the local charge distribution from the macro dipole. In this way, simplify what is done in the deep potential, which requires for you to already have this local charge distribution. And then we correct for the electronic polarization as a macroscopic effect. And this model we are getting actually predicts this long-range electrostatic potential with great accuracy. And we are hoping that this is a step towards where we want to run this voltage-controlled molecular dynamics using machine learning potential. So again, this is now available online as a preprint. And if you are interested, you can scan this QR code. So now I'm at the last slide to acknowledge the people who have worked on this. So Xiang and Christoph worked on they were the lead on the project of the lithium field evaporation. And here, this is a team of the electrochemistry group, especially Samuel, who did a lot of the actual calculations with the VASP-python plugin. And on the VASP side, the main helper for us was Sudarshan Vijay. He is the main developer of the VASP-python interface, and we had a lot of back and forth discussion to really figure out how to include this external potential into our simulation. And here are the funding agencies. Specifically, I'm personally funded by the Alex Humboldt Foundation. And with that, I thank you for your attention. And just want to say again that it's a great pity that I cannot be there due to the visa complications. And as you can see, these studies are quite recent, and your feedback is greatly appreciated. If there is any question that I cannot address in this 10 minutes Q&A, Mira and Jorg are also very familiar with the details of this work, and you're welcome to approach them. They can explain as well as or probably better than me. So thank you for your attention.